important thing about this method is this method can be used for a multi-story frames. So that is the advantage of this method. Whereas in the previous two methods, what you have done, it is applicable. That is the slope deflection method and the moment distribution method. It is applicable only for the simple beams, continuous beams, one-side beams, or the frames. Whereas in this method, you can use this method for any type of frames, whether it is multi-storied or two bays or any type of beam. Now, what type of beam are we talking about? You can see here. So in this Carney's method, so this is the regular beam which I've already studied. Okay. So where it can be used? Especially in the frames. Now you can see here, these are simple beams. Things are easier. It is mainly used in the frames wherein there are double story, multi-storied. Okay. Now see here, this is one, this type of frames you have already solved. Okay. Now you can see here, this is complete frame. Okay. This frame has two stories. Suppose this is like a ground floor and this is like the first floor. So the advantage of this Carney's method is you can solve multi-story beams, multi-storied beams, multi-storied columns. Okay, you can. This method is applicable for such type of frames. So you can see here this A, B, E, and F. Only this lower portion. Okay, this is called as bay. Okay, lower portion it is called bay. If I add one more here, okay, if I show you one more. Okay, now see here. A, B, E, and F. There, this is called as one bay. Okay, this is complete. Or A, C, D, and F. This is called complete. This left portion is called a bay. Okay, this is one bay. Then F, D, J, and G. This is called second bay. BAY. That is called as bay. So this is one bay. This is second bay. So these are called bays. These are called stories. This is first single story. This is for second story. So if I add one more frame here, it will be third story. So as you go on increasing the height, you go on higher like this, those becomes the stories. STOREY. So those are called as stories. And this as you go vertically, they become story. As you go horizontally, they become bay. BAY. All right. So if the problems are as such, you cannot solve this by moment distribution or slope. Okay, so this is called as a story, and this, if you go horizontally, that becomes the bay. Okay, all right. So the steps are more or less the same. So first thing is we'll be calculating the. So suppose this is a given beam. So it is same. A is fixed, D is also fixed. Okay, and as usual, first step is fixed end moments, finding of the fixed end moments. That is A B C C D. Okay, you'll be calculating the fixed end moments. The next step, what previously we had done was in the slope deflection method, we used to use the slope deflection equation to calculate that, and in the second step, and in moment distribution method, we used to calculate the distribution factor. Okay, all right. So here, what we do is in this Carney's method, the first step is same, that is finding the fixed end moments. Second step is finding the rotation factor. Now, what we used to call previously as distribution factor, now in this method, we'll call it as rotation factor. Okay, the formula is more or less the same. Okay, see here, what is to find here in the moment distribution method was distribution factor, that would be K by summation K, right? Here, rotation factor is same, K by summation K, but it is minus 1 by 2, minus 1 by 2. So it is minus 1 by 2 KAB or by summation K. So you're again multiplying this with minus 1 by 2, or it's called as minus 0.5. Okay. So that is what you're going to find in rotation factor here. Second step is same. So you see here. So rotation factor, same thing again, joint, members, K, summation K. But here the formula becomes, so rotation factor is equal to minus 1 by 2 K by summation K. Okay. So in moment distribution, you used to only find out K by summation K, you used to write off in this column. Now the rotation factor is, you're just multiplying with another factor, that is rotation factor is equal to minus 1 by 2 K by summation K. Okay, that is what table you have to find out here. So first is simple, first step is same, that is finding the fixed end moments. Second step is finding the rotation factor, and next rotation contribution. So in the previous method is to write it as moment distribution table, is to find out moment distribution table. Here we'll find out rotation factor. Now how to draw this rotation factor here, I'll just tell you. Okay, how to draw that. See here, first thing as usual, we have to draw the beam. Okay, so you can see here. Hmm. Now see in this portion. So it is A, B, C, and D. So you're finding the rotation factor only at joint B and C, because those are the joints which connect BA also, BC also. Likewise, at C it connects CB also and CD also. Okay, so now this B and C will have the rotation factors here. That is what we're going to show it here. Now see here, how we'll be drawing it like this only. That is. You can see first A, only where there is a rotation factor you have calculated, that particular joint you have to draw two boxes here. One is the big box, next is the small box. Similarly at C, you have to draw the big box and small box here. Then at D, as usual, show it as a fixed end. Okay, all right. Now what to write in this is important. Now see here, you have calculated fixed end moments here initially. Okay, so all the fixed end moments should be shown here. So at A, MFAB, you have to just draw. See, it is like a beam. Okay, only you're going to magnify joint B and C with the boxes. All right, so at joint A it is minus 10 plus 10. Again at BC is here minus 58 and the CB is 71. So this is minus 58, 71. Next, CD and DC is minus 20 plus 20. Okay. All right. Now, once you mark all this, you should mark all the fixed end moments outside like this, outside the box. Now, what you write inside is, let's see here, BA. So BA is nothing but fixed rotation factor. Okay, so BA, rotation factor of BA is minus 0.214. Okay, so it is minus 0.214. You have to write in BA. See here, B. So when you split this B here, if you cut this exactly half, so left of this B becomes BA. Right of this B becomes BC. Okay, so now this is BA. So BA, whatever is the rotation factor here, so mark it here. So it is minus 0.214, which is minus 0.214. Similarly, BC. So BC is minus 0.285. So in this portion you have to write. And always try to write this vertically like this. Because if you try to write horizontally, the page won't be enough. That's why it's important for you to just write it vertically. Okay. Next, similarly in CB, again left side of C is CB connecting. Right side of C is CD. Okay. So now here CB is 0.285, 0.285 and CD is 0.214. CD is 0.214. You have to write it in this portion. So all these are nothing but the rotation factors what we have calculated here. Okay. Hmm. Next, within the small box, you're going to write, now see, just adjacent to the box, whatever fixed end moments are existing adjacent to the box, that is left side of b, right side of b. Now to the left side of b it is 10, to the right side of b it is minus 58.33. So you need to add both of these. So 10 minus 58.33 is minus 48.33. So that is the one you're supposed to write it here. All right. Similarly, 71.67. So again in C, left side of C is 71, right side of C is immediate left side of C, immediate right side of C. So it is 71.67 minus 20 is 51.67. So there, this and this you're supposed to add and write. Okay. Similarly here, this and this you're supposed to add and write in the short square, small square. Okay. Okay. So later I'll tell you how to do this iterations. All right. So once you carry out all the iterations, okay, within 3-4 steps, all right, then you need to directly calculate the fixed end moments, near end, far end, and final moments. Okay. The most important, see, when you're calculating the final moments, it is fixed end moments plus 2 times near end contribution and far end contribution. Okay, this I'll further tell you when I explain in the example problem. So as of now, what you're supposed to know is the steps and all the same. So first step is finding the fixed end moments, which you have done previously. Then finding the rotation factor, again that you have done previously using this formula. Only thing you need to add for this is minus 1 by 2. That is nothing but minus 0.5. 1 by 2 is 0.5. So it is minus 1.5. You have to add this in this column. Once you get the rotation factors, those rotation factors should be shown here. Okay, again this should be drawn same like a beam. So end A and end D as fixed. Only B and C, okay, joint B and C should be magnified like this with the two squares. Okay, again two squares should be drawn. In first bigger square you're supposed to mark the rotation factors here, which you have found here previously here. Okay, so that is BABC, CBCD, and then just immediate left side of this B and the right side of the B. You have to add both these fixed end moments and write it in the smaller uh, box. And then same thing with C, left side of C and right side of C, those fixed end moments, you need to add both of them and mark it and write it in this column. Then further iterations, I'll tell you with the example problems. Okay. A drawing this is very important in Carney's method. Okay. Once you understand this, these things are simple. Next is just carrying out the iterations, applying the formula. All right. Okay. So that's all for today. Okay. Thank you.